Hi, I'm Asia Brown, and we did Chemistry Chapter 4, Atoms and Elements. Elements are pure substances from which all other items are built. They cannot be broken down into simpler substances. Chemical symbols are one or more abbreviations for the names of each element. On the periodic table, the elements are arranged into similar properties. Periods are horizontal rows of elements from top to bottom on the table as periods 1 through 7. The periodic table organizes 118 elements into groups and places them in order, increasing the atomic mass. Group numbers are written at the top of each column. The letter A is for representative elements, groups 1A through 8A. The letter B is for transition elements, groups 3B to 12B. An alternative system assigns numbers 1 through 18 to all groups from left to right across the periodic table. Next up, we have Kiana.
Hello, I will be discussing the atom. The atom is the smallest particle, and Dalton came up with the atomic theory, which states all matter is made up of tiny particles called atoms. All atoms of a given element are similar to one another and different from atoms of other elements. Atoms of two or more elements combine to form compounds, and a chemical reaction involves rearrangement, separation, or combination of atoms. Continuing on with Dalton's atomic theory, people cannot see the atom with the naked eye. However, they can see them when billions of atoms are combined together. As an example, a single nickel atom versus a nickel, which we use for currency. The structure of the atom. Subatomic particles consist of protons, neutrons, and electrons. Protons are positively charged subatomic particles. Neutrons are neutral, and electrons are negative charged particles. Ernest Rutherford discovered the nucleus and its mass. Protons and neutrons are subatomic particles that are found in the nucleus. Electrons are found on the outside of the nucleus, and the weight of the atom consists of the nucleus. The mass of the atoms is measured in atomic mass unit, or AMU. And next we have Portia.
I will be talking about atomic number and mass number. The atomic number is equal to the number of protons in an atom. It is a whole number, and it is also found on the periodic table above the symbol of an element. The number of electrons is also equal to the number of protons, which means it is also equal to the atomic number. Every atom has a net charge of 0. And here is an example of finding the number of protons or electrons in a certain element. So as you can see, 47 is located above the symbol, which means this is the atomic number. That means that there are 47 protons and 47 electrons. Okay. The mass number is the total of protons and neutrons in the nucleus. It is not located on the periodic table, and it is also a whole number. To find the mass number, you add the number of protons to the number of neutrons. If you are given only the mass number and the number of protons, you can subtract the protons from the mass number to get the number of neutrons. This is just an example. If 9 is the mass number, 4 is the atomic number, so you would subtract 4 from 9 to get the number 5, which is the number of neutrons. Section 4.5 talks about isotopes and the atomic mass. An isotope are the atoms of an element with the same atomic number, but a different number of neutrons. To tell the difference between the isotopes, we use an atomic symbol, which is written in the upper left-hand corner. The atomic symbol represents the mass number. So in this example, 2 is the atomic number, 4 is the mass number, and this is the symbol. The atomic mass is the weighted average of all the masses in a natural isotope of a particular element. The only way to calculate the atomic mass is to be given the percent of abundance, but that can only be found experimentally. And you would multiply the percent of abundance by the mass of the isotopes. And now we'll have Kristen.
Hello, my name is Kristen Rouse, and I am going to be talking to you about 4.6, which is the electron energy levels. And electromagnetic radiation is something that we use every day, and it is much more than meets the eye. Electromagnetic radiation includes radio waves, gamma rays, X-rays, which is at the end, and also visible light. Visible light is the section right through here that covers 308 nanometers to 750 nanometers, and visible light is what we can all see. We measure the different waves to identify the type of electromagnetic radiation, and that is called wavelengths. The wavelengths go across this way, and there is more energy when you get to the fast wavelengths at the end. Sunlight will shine through a prism and show us light and colors, and similarly, light from a heated element separates with colors and darkness in between. And this is the individual atomic spectrum, and every element on the periodic chart has its own individual atomic spectrum. These atomic spectra are connected to changes in electron energies. And you can see on the chart at the bottom here that when an atom is receiving wavelength from the sun, it gets excited. So its absorption of the energy makes it move to another shell. And then when it releases the energy, it moves back into its what we call a ground state. Scientists have learned that the lines in the atomic spectra are connected to the energy levels in the atoms. If you remember, in an atom, each electron has its specific energy level, the lower levels being the lowest energy, and the highest being the higher energy. There can be changes from a lower energy level to a higher energy level if the electron absorbs the energy. In the electron arrangements, the number of atoms in each energy level are given by the electron arrangement. And as you see on the periodic chart in 1 through 20, and as Asia mentioned in her presentation, the groups list the number of levels of energy that they have in their periodic chart. And just to link what we see here to everyday life, we use UV light in health implications and treatments for diseases like psoriasis, and also to excess vitamin D from the sun. Now I'm going to turn this over to Margaret.
I'll be talking about section 4.7, which is trends in the periodic properties. So what is a trend? A trend is a general direction in which something tends to move. Periodic trends are specific patterns that are present in the periodic table that illustrate different aspects of a certain element, including its size and its electronic properties. Major periodic trends include electronegativity, ionization energy, electron affinity, atomic radius, melting point, and metallic character. Periodic trends arising from the arrangement of the periodic table provide chemists with an invaluable tool to quickly predict an element's property. These trends exist because of similar atomic structure of the elements within their respective group, family, or periods, and because of the periodic nature of the elements. So now I'm going to talk a little bit about these different trends. Electronegativity, it can be understood as a chemical property describing an atom's ability to attract and bind with electrons. From left to right, across a period of elements, electronegativity increases. From top to bottom, down a group, electronegativity decreases. And this is because the atom number increases down a group, and thus there is an increased distance between the valence electron and the nucleus, or a greater atomic radius. There are exceptions to this rule with the noble gases. When we look at ionization energy, It is the energy required to remove an electron from a neutral atom in its gaseous phase, and is conceptually the opposite of electronegativity. The ionization energy of the elements within a period generally increases from left to right, and this is due to electron shielding. When we look at electron affinity, as its name suggests, it's the ability of an atom to accept an electron. Electron affinity generally decreases down a group and increases from left to right within a period. And then also when we look at the atomic radius is 1/2 the distance between the nuclei of two atoms, just like a radius is half the diameter of a circle. Atomic radius decreases from left to right and increases from top to bottom within a group. We also look at melting point as a trend, and melting point is the atomic energy required to break bonds to charge solid phases of a substance to a liquid. Also, metallic character. Metallic character trends of an element can be defined as how readily an atom can lose an electron. Metallic character increases from right to left across a period, and it also increases as you move up and down a group. The elements on the periodic table show many trends in their physical and chemical properties. Across rows, periods, or series, down the columns or groups of the families. Atoms with the similar properties appear in groups of families in the vertical columns on the periodic table. So, when we look at metallic character, it decreases and increases down a group. Atomic radius decreases across a period and it increases down a group. Ionization energy increases across a period and decreases down a group. When we look at ion size, it decreases across a period and increases down a group. And electronegativity increases across a period and decreases down a group. This completes our project for today. Thank you for listening, and we hope you enjoyed it.
Thank you for watching our presentation, but we couldn't leave without giving you some information about where you can go to study more about chemistry. Here are some websites, so please take a moment to write the names of these websites down. These websites contain interactive games and quizzes and puzzles and different types of things to make learning chemistry fun. Thank you.